Last topic for environmental chemistry, wastes. Let's look at air pollution. The winds, so the source of point source or non-point source, maybe in one place, but it can show up in many other places. So within our air we're looking at here. So we could look at something like smokestacks or from industrial production, factories, etc. Those would be point source. And non-point source, something like maybe ash from forest fires or other pollutants, like we were looking at radiation when Japan had the earthquake. We can see these pollutants moving throughout our environment. So the three stages of transport of substances in the environment are the release of chemicals at the source, the spreading of the chemicals into the atmosphere, and the deposition of that chemical into the soil or water. The direction and distance that the chemical travel can vary based on where it was released and what the wind patterns are there. Wind patterns bring more airborne particles and pollutants to higher latitudes, concentrating them up there. We can see that the air circulates upwards in our globe. Okay, so above the 30th degree, these things are moving upwards. This concentrates them up in the north. And then when they fall as snow, these pollutants are concentrated in that snow or water. Water pollution. Water pollution is when chemicals can enter the surface water and the groundwater in many ways. A substance that dissolves easily can be carried far by the water and spread over a very great distance. Substances that maybe don't dissolve as easily may sink to the bottom of wherever they're introduced and become more concentrated closer to that source. Water quality is monitored regularly, and wastewater and sewage must be treated to reduce harmful effects before being returned to the water system. So using chlorine or UV light to destroy bacteria and viruses is a start, but that's not all. Sewage treatment in urban areas, there's 3 steps: the primary, secondary, and tertiary. In the primary step, this is where we are physically filtering, settling, etc., trying to remove solids and any suspended particles. In the secondary, we're removing biological organisms, so bacteria and microorganisms decomposing most of what is organic waste. Then this organic waste can be recycled as fertilizer, and we use UV light and chlorine to kill any remaining organisms. Tertiary is where we add chemicals, and remove chemicals depending on what kind of wastes we are treating. In tertiary, we are removing phosphates and nitrates. Again, remember, those are not good for our water supply. By percolating them through the soil into the groundwater using a lagoon or a marsh. Plants in the marsh can even remove some heavy metals. So just a different way of filtering and removing particles. Here's a picture of it. So in our primary, we are screening and allowing settling, and we collect that settling. In a secondary, this is where we are allowing microorganisms to decompose any more organic waste and filtering those out and collecting them for, again, could be used for fertilizer. We're also treating with chlorine and UV light at this point. In tertiary, we are stripping the nutrients that are not good for our water supply in filtering beds or some sort of filtration device, whether that is a lagoon or a marsh or maybe a man-made thing, to try and remove phosphates and nitrates and then releasing that water back. Sewage treatment looks different in a rural setting. Typically, we have a septic tank, which is a large underground container that traps grease and large solids that can periodically be pumped out. But it's not just held in a septic tank. Liquid waste is distributed through pipes with holes that are perforated, the pipes leading to a drainage area with gravel. Bacteria and other microorganisms in the gravel and soil break down the organic waste and use it as a source of food energy. This system mimics the way in which decomposers normally recycle biodegradable wastes. So looking at it here, we have our septic tank connected to our household water. Again, the septic tank often will have some separation occurring. Liquid sewage is pumped out into the septic system, into these pipes. It's allowed to drain into the crushed gravel, and microorganisms break down the organic waste there. Groundwater is water that soaks into the soil and collected in some sort of zone is the groundwater zone. Water filters through the soil and cracks in the rocks. Contaminants can remain collected in the groundwater for long periods of time, though. So we see that water is soaked in underneath, and we can see the water moving into this groundwater area. We don't want contaminants being concentrated here because this is our water supply to homes. Groundwater can also come out in rivers and our water systems, so we don't want it contaminated. Again, it can cause problems if the groundwater is used for drinking, agricultural purposes, or industrial use. We don't want to see contaminants in our groundwater. Groundwater moves sideways, up or down, and can move slowly or quickly. So we can see it move across the land, it can soak into the land, but it can also come up into our water systems. Groundwater, again, usually joins rivers and lakes eventually. Groundwater movement depends on the number and connection of pores. So how tightly our soil is packed, what type of soil is there, etc. Non-connected or tightly packed pores means that the soil is impermeable. The water cannot flow through. Connected pores, the soil is permeable and water can move through it easily. Permeable ground can create what we call aquifers. An aquifer is a pocket of water below ground that is separated by layers of rock. Water is naturally filtered through the soil and enters this underground aquifer. It can produce useful amounts of water when a well is drilled into them. But contaminants that can dissolve in the water and become concentrated here. Deeper aquifers, which are confined, are often less contaminated because of the layer of clay up top. So this layer of clay here acts as a bit of a barrier. Therefore, a confined aquifer is likely more pure than a water table well or an unconfined aquifer. So unconfined can become more contaminated than a confined simply because of this layer of clay that is impermeable to water. Ground pollution. To reduce ground pollution and pollution in general, we want to follow the 3 R's. Reduce, reuse, recycle, and recover. Reduce is the best. We're going to use less of a certain product. Again, it's the most preferred option because we just don't make as much waste in the first place. Reusing products, again, instead of throwing them away, can keep them out of our landfills. Recycling, using it in a new way or melting it down and reusing in some different way, again, can keep things out of our landfills. And lastly, recover. Breaking down the product into its original elements or compounds. So recovering metals is often, or elements is what we're looking at here. What isn't part of the 4 R's gets disposed of in a landfill. A sanitary landfill. Landfill problems include wind, so carrying garbage, scavengers getting in there, and disease, leaching into groundwater, as well as methane and carbon dioxide gas production. So to reduce these problems, our landfills are covered with a layer of sand each day, it's permeable, so that the garbage does not blow away and is contained for scavengers. Landfills are also lined with clay to prevent this leachate from affecting groundwater. So leachate is the toxic liquid soup that comes from decomposing garbage. And we want to keep that out of our groundwater as much as possible. So we're going to contain this within clay, which remember is kind of impermeable. Carbon dioxide and methane gas can build up over time, which causes safety concerns. So decomposition produces these two gases. Therefore, we collect it and we can actually use it. Here's again a description or a picture of a sanitary landfill. We can see that we have a clay layer. We have pipes that are collecting the leachate from the bottom of a landfill, and then we can treat it like we would treat our wastewater. Our solid waste is packed in, and we have a layer of clay up top in the end, sand and topsoil, just to protect this and to keep it contained. We also see that we have a methane gas pipe here. The pipe can collect this methane gas, and it can be used to produce electricity. We can see that it's contained. It is not affecting our groundwater, and we are looking to always make sure that it is staying within the barriers we've provided. A secure landfill is just slightly different. It's used to store and dispose of toxic or hazardous chemicals. It is also lined with clay, but also with plastic to prevent leaking. Leachate is again collected to prevent contamination. So we have this actual liner implemented here as well. And we're not looking at the production of gases. We are just basically storing this hazardous waste. It likely won't break down. We are trying to just keep it contained. Hazardous wastes are any type of waste material that is considered poisonous, toxic, corrosive, flammable, or explosive. Improper storage or transport and disposal of these products can contribute to burns, heart problems, kidney failure, lung and respiratory ailments, cancer, and even death. So whether we are handling them or whether they are present in our environment. Many households' hazards are cleaning products called solvents. A solvent is any substance that can be used to dissolve another substance. So we use HHPS. HHPS stands for Hazardous Household Product Symbols. And again, these are probably on the cleaning products and other things you find around your house. They have different levels of warning. So we have caution, which is the lowest, and it would be a yellow if there were colors involved. Triangle. Then warning is orange diamond, and danger is a red octagon. And we can put whatever symbol we would like within each. So poisonous, flammable, and explosive or corrosive, and then based on how much caution we should be using. So how have we improved our release and treatment of pollutants in our environment? We've looked for biodegradable things. Biodegradable is a product that will break down naturally over time. Some things degrade into microplastics, though, not organic compounds. So the example here is compostable bags. Compostable bags are made of plant materials and break down during the commercial composting process into non-toxic components. So a compostable bag will make water, carbon dioxide, and some sort of biomass that is easily degraded by bacteria in our environment. Biodegradable bags simply have additives that over time will break plastic down into smaller size pieces, but those still take many decades to disappear. So a biodegradable doesn't mean that it will create organic material. Biodegradable simply means that it is making smaller pieces of plastic. Biodegradable bags are not compostable and will contaminate green organics bins, so be sure that you are using the proper bag if you are actually composting, and just know the difference between compostable and biodegradable. They are not the same thing. Know that some products break down faster than others. Biodegradation occurs because of living things. So earthworms, bacteria, fungi, microorganisms, they all work together to break down our products. The speed at which things biodegrade depends on oxygen in the soil, the temperature, moisture, pH, and nutrients available there. Some other ways that we can break down our chemicals is photodegradable plastic. It's made of chemicals that react and break down when exposed to sunlight. In 3 months, the plastic becomes a fine powder that is easier to dispose of. This type of plastic will only degrade if it is exposed to sunlight. If it's buried, it will last in its original shape for hundreds of years still. So we can see a water bottle that is photodegradable working to break down. Remember, there's still microplastics here. It's just not in its same exact shape. Bioremediation is using biological organisms like plants, bacteria, microorganisms to solve an environmental problem such as contaminated soil or groundwater. These organisms can remove or reduce the effects of pollution or a toxin. For instance, in an oil spill, there's oil-degrading bacteria that can be used. However, it takes a long time. So we see, it's a little bit blurry here, but a hydrocarbon from the oil. The oil is surrounded and attacked by these hydrocarbon-degrading bacteria, and they break those into CO2 and water. So the CO2, of course, is released into the atmosphere, water is remaining, and we just get this byproduct that is broken down, and it is no longer that hydrocarbon or oil that would have been problematic. A bioreactor can also be used. It's a tank containing bacteria to treat polluted groundwater. Phytoremediation is pretty cool. Plants have been used to clean up metals, hydrocarbons, different solvents, pesticides, radioactive materials, explosive, and landfill leachate. The plants are able to absorb large amounts of these chemicals and keep them within themselves. When the plants have matured, they are harvested, burned, or composted. In some cases, they can actually extract the metal back from the plants and recycle it. When most of the harmful chemicals are removed from the soil, then other plants can be used. A big example of this is sunflowers. Sunflowers can absorb radiation from the soil. So sunflowers were planted around Chernobyl and the nuclear plant in Japan that was affected by the earthquake to remove radiation in the soil. Those plants then have to be disposed of properly though. For the practice, complete this learning guide, and there is some extra practice on page 252 of your textbook. Don't forget there's also a unit review if you're looking for extra practice to practice for your unit exam for environmental chemistry. That's listed on the environmental chemistry exam page.